Hello. Okay. The only trouble that students don't attend. Oh, but you can attend lecture without mentor. If you save this link, it is the same for each time. Meet Google Come. This. This link is name of my classroom. So you can save it later. Good afternoon. So next time I made in such way. I save it. I save it in Google, and after that I can attend each time without mentor. Okay, let's start. So this class is about how to calculate input shaft bearings. Input shaft bearings. So this is a gearbox HH11. One input, one output, and into the gearbox we have input shaft which connects half coupling and engine with pinion. And from pinion, power is transferred to the wheel and to the output shaft. Maybe like this, or maybe just a moment. The same idea, it's vertical VH1, 2, and here we have the same design. Input shaft, which is the same with pinion, the same material. We have two bearings, oil seal, cover, key. We selected their previous class, I mean the bearings, ring nut, oil seal, and key. And I shown you how to draw input shaft and how to find distances, because when we calculate input shaft bearing calculation, first we need distances A, B, C between elements we discussed previous class. I show you one more. It is a fragment from our previous class. and here we have a distance A, B, and C. We found that distance A is approximately 80 millimeters, and distance B, it is a distance between middles of bearings, and this distance is recommended approximately 2D, where D is a bore diameter of bearing. So it is a diameter where our bearing is mounted on the shaft. So if in my case, in my example, diameter of the bore is 40 millimeters, so this distance will be 80 millimeters. It means that approximately the same like this distance. So this distance 82, 84 millimeters usually, and here 80 millimeters. This distance was 32, 34 millimeters. So in such case, we know distances A, B, C. We can measure there from model, from drawing, anyone. But we need some another parameters to calculate bearing load capacity or required capacity. First, torque, T input, table number 3. Then rotational speed, revolution per minute, and input, table 4, or table 7, also you can use it. Pinion pitch angle from table 7. This is a table 7, gear calculation, page 5. Here you see torque, rotational speed, pitch angle, and after that dm also from table 7. dm1 means that it is for pinion. We can use dm2, but in such case you should use t2, t, n out, t out, and delta 2. Better for first calculation for input shaft bearing, better if you use this subscript 1. Then distances, you measure your calculations, and the first approximation, you can take B distance, I said, like 2 bearings bore diameters. In my case, in my example, it's 80 millimeters. Here we selected bearings, and inner diameter, bore diameter, is 40 millimeters. I hope you have it. profile angle alpha is 20 degrees, and bearing code dynamic and static load capacity you can rewrite from table 11. We considered one bearing because from technological reasons it is better calculate both bearings. After that, select most loaded and select code and dynamic load capacity according to the maximum load, and use the second bearing the same like calculated. That's why we consider one code and dynamic and static load capacity for this bearing. Then force diagram. Force diagram for all tasks the same, the only difference is distances. Let's consider. You should know from our course that in a barrel transfer we have three forces in a contact. Red is tangential force, blue is radial, and green is axial. And one more force we have here. It is a force which is applied from half coupling to the key. This force is not known in value, and what is the place of application and what is direction. So we consider it some later. So we see that forces radial and axial both act in one plane. Usually we consider like this. We consider these two forces, radial and axial, in so-called vertical plane. It is conditionally known like vertical because point of contact may be here, maybe here, maybe here. For example, in such case, contact here and tangential force is perpendicular to the plane of screen. And in such case, this force is horizontal. And radial force and axial force are in vertical plane. So we consider this state conditionally, and we name plane where axial force and radial force are act. This plane will be named like vertical, and this plane where we have tangential force and coupling force, they are in a plane perpendicular, which is perpendicular to top plane, front plane. So and this plane will be horizontal. One more, this conditionally known force planes. The only feature of this plane, these planes, that they are perpendicular one to another. For example, it may be like this, but we can turn it 90 degrees and we will have tangential force horizontal, vertical, and this and horizontal. So it does not mean that we consider a relative state. We consider its conditionally. Okay, so after this consideration, we come to calculation. So this diagram is general, and you see here F coupling, F T tangential, FA axial, and FR radial. FA, it acts on a dm diameter, and if we move FA to this axis, we'll create moment, bending moment. So in vertical plane, I repeat that vertical is a plane where axial and radial force act. So FA times dm divided by 2, it will be m. Here a point of contact, so m green is a moment which acts at this plane. And in horizontal plane, we have tangential force and F coupling. So it looks like here. And I remind you that according to equilibrium conditions for horizontal plane and for vertical plane, we create equations where we have to consider all forces in each plane. For example, for horizontal plane, we have force Ft and Fc. Sorry, it's my dog cry for my wife. So, distances A, B, C, and force times distance create bending moment. So the same picture, summary moment is calculated like this. And according to these equations, we'll have radial reactions in vertical plane and horizontal plane in points A and B. Moment, radial force and tangential force creates like this. Then, what is the FC value? value. For jaw compression coupling, which we used for this connection between engine and gearbox, it may be this force can be calculated like this. This force is not force which is transferred from engine to coupling to pinion. It is a force which may be considered like additional load for our transfer, and it may be calculated according to experiments from equation like this. But usually from this force only 10% may be used for calculation. So FC is 0.1, 10% from this force. Then let's consider this formula. Tangential force Ft in a table 7 Ft tangential force in table 7 dm mean pitch diameter here then radial and axial forces. Oh my god. Radial force tangential times tangent alpha 20 degrees. Tangential of 20 degrees is approximately 0.364, and the axial force the same formula, sine, here cosine delta, here the sine. Tangent alpha the same, sine and cosine of delta delta. Delta this pinion pitch angle. Sorry, just a moment. I'm here. Then, and I said that coupling force may be calculated like this. Ready? Bending moment FA times dm divided by 2 in Newton millimeter. Newton millimeter. And after that we can find radial reactions in a point A and a point B. Formulae for reactions you can use from this example. So you can rewrite this formula and after that calculate according to your values. Pay attention that some reactions may be negative. Negative means that this reaction is directed in a direction opposite to selected previously. If this reaction is negative, it means that it is directed down. And after you find reactions in point A and in point B, we can find summary reaction. This reaction is RA and RB according to this formula. And you see that reaction in point A and point B are different, and in point B 3.5 times greater than in reaction in point A. So I told you that better if we use the same bearings for both supports. In such case, one of them will operate under the load, another one will be loaded 3 times less. Who is it? Wow! Jurabek, it's you? Surprise. So, but we calculate support B load capacity, required load capacity, and we'll select bearing according to this load. One more. This reaction is load on a support. It is not radial force, it is radial load. Because in this calculation we use radial load and radial force. Radial force is here, radial force. And in this table, FR, it is not radial force, it is radial load on a bearing. 53, 55. Here, it's So, how to calculate required dynamic load capacity? First, let's show you. Strain condition looks like this. C, it is a calculated load capacity, dynamic load capacity, should be less than catalog value. CC, it is a catalog value of load capacity. So if we calculate according to service life should be greater than catalog that we have in task. So we need to find catalog value and calculate it. Catalog value we found previous time, so we know what is it, what's value should be. So now we need to calculate C, required load capacity. It may be found from this formula. Pay attention here, P small and P capital, they are not the same. P small, it is an exponent for ball bearings, free for roller bearings, 10 by 3. And P capital, it is an equivalent load. You see that this formula, we have two parameters. Looks like the same, but are not the same. And L, it is a service life in millions revolution. In millions because catalog value is a value which under this load bearing should operate 1 million revolution. So that's why we need to know service life in millions. It may be calculated like this. Here, N, it is a rotational speed. It is known. LH, it is a given data. And in such way, we can calculate L. So, A1 and A23, two coefficients. A1 is a factor considering reliability. Reliability, normal reliability is 0.9. It means that 90% bearings can work during 1 million revolution. And if we need to increase reliability, if we use bearings in a place where their damages may create tragic sequence, so we need to increase reliability. In such case, A1 decreases, and it means that we have bigger bearing. You see, A1 is a denominator, and when it is less than 1 and decreases, in such case, C increases. So the bigger S, the bigger value C, the bigger bigger bearing we need. So let's take, I took it 1, so for reliability 0.9. Operating condition factor A23. Factor A23 for usual condition should be taken from first column. For our case, when we use ball bearings, it may be 0708. If we change type of bearing, for example, not on the tapered roller bearings, we can use from this table, from this value. So 0708 approximately. So let's take it 08. Service life in millions of revolution. I shown you this formula 60 times n times LH. Pay attention that n, it is a input shaft rotational speed, the higher value, and LH should be in thousands, in hours, so with zeros. In such case, it will be correct. Usually this value more than 1,000, so it's very big value. And I remind you that this parameter we used in calculation of gear transfer, and if you calculated transfer by my software, you can see in a final results this value the same like for contact stresses. So exponent, I said that the ball bearing should be free. Rotation factor. V is rotation factor. In our case, when inner ring rotates and outer ring is fixed in a fixed path of support, in such case V equals 1. If outside ring rotates, in such case V is 1.2. But in our task, in all variants, inner ring rotates, that's why V equals 1. KB, it is a safety factor. In a case of light load 1, medium load 1.3, 1.8, and with heavy load 2, 3. Let's consider something average. Let's take from this region. So KB, I took 1.3. Then KT. KT is a temperature factor up to 125 degrees centigrade. It is 1. In our mechanism, we use mineral oil, and mineral oil operating temperature should be 80-90 degrees centigrade. So it means that the bearings also will be with a working temperature less than 100 degrees centigrade. That's why KT in our case equals 1. KT 1. So what about axial load factor? Here we consider so-called axial load factor. This factor shows us should we take into account axial load or not. So we should first calculate load criteria, Fa divided by VFR. Fa, it is a radial force, axial force. Fa, it is an axial force. Fa 269, why 269? Oh, 282, I should correct it. And V1 and Fr, it is a radial load 3004. Very big difference between radial load and radial force. Radial force in our case 800. Radial load 3000. So more than 4 times, approximately 4 times different. So this value in our case, in my case, is 0.007. Axial load factor, table for free, axial E is minimum value is 0.90. The minimum value is 0.90. That's why if criteria, load criteria 0.07 less than axial load factor 0.19, in such case load factor radial x and axial y are 1 and 0, one more. If Fa divided by VFR and less than E, x is 1, y is 0. It means that Fa smaller, very small, and we can neglect axial load in bearing calculation. 0.19 means that it's approximately 20%. If Fa less than 20% from radial 1, in such case we can use x1, y0. It means that we use radial force only, radial load only. We don't take into account axial. But if this value more than E, x 0.56, y should be calculated according to relative load. But in our case, it's usually x1, y is 0. That's why it's written here that load factor x and y, 1 and 0. After that, we can take this parameter and calculate equivalent load. I remind you that P capital is the equivalent load. In this table, exponent P small. But now we consider P capital. This formula is general. General means that we can use here sometimes radial load and axial load. But if x equals 1 and y equals 0, it means that and we should use fr only if a is neglected. So v is 1, and finally we have formula like this. Equivalent load, it is fr, it's radial load, times kb, because kt is 1, v is 1. So in this formula, 1 f radial plus 0 f axial times 1.3, 4,400, 500. Then, when we know load, equivalent load P, we can find dynamic load capacity. It's required dynamic load capacity. This formula I have shown you. L, it is a service life in millions. A1, 1, A2, 3, 0, 8. That's why here 1 times 0, 8. P is free, 1 divided by P means that it's cube root from this value, and times equivalent load. And finally we have dynamic load capacity approximately 50,000 Newton. So very big value. Now we should consider strain condition. In my case it is not satisfied because load dynamic catalog dynamic load capacity is 32. We need 49. Oh, what we should do in such case? Then so 49 much greater than 32. There are some ways how we can solve this problem. First, change bearing and take it 408. Let's consider bearings. It is a standard, it's a catalog values. We used previously 208. I remind you that two last digits times 5 gives us diameter. That's why give times 5, 0.8 times 5, it's 40. All of them has 0.8. So 208, 32 is not good for us. We can take it greater. 308, it's medium series. 41 is not enough. 408, 63, it may be. So 63 outer diameter 110. It's very big. You see, this is a initially designed input shaft B80 and two bearings 208, but it is not enough in our case. If we replace bearings, you see that how it looks like. Here should be much bigger cover, bigger should be bigger sleeve, so it is not beautiful. But maybe it's second way. Increase the distance between supports. $100 and T208. Or we can change shaft diameter and instead of 208 take 309. Increase shaft diameter up to 45 and use bearing 309. Here you see three variants: 408, increase distance and change diameter. But it is not far long. Sorry. Another variant is, just a moment, we can change type of bearing. And instead of ball bearing, use a roller bearing. It's so-called tapered roller bearing. And for example, for our case, diameter 40, 08, 08, 08, but as minimum, we have load capacity 46.5, close to 49. So you can use this bearing and increase distance B, for example. You can take bearing A, means that high quality. 58, it's graded at 49, it's maybe or we can use, instead of light series, medium series, and you have load capacity 56, also graded at 49. In such case, if you replace type of bearing, you should recalculate some parameters. For example, instead of 3, it should be 10 divided by 3 here, and A23 should be smaller. In such case, usually load capacity less and required load capacity, the required load capacity, and you need bearing lighter that it was in a case with ball bearing. So can be such way. Of course, we can use another solutions but after you calculate and draw sketch, you'll see is it beautiful or not. If it is not beautiful, we can find more beautiful solution and make it better. So that's all how to calculate load capacity. Now you can ask me your questions. So, um, you can, I record this class and you can use it in our 202 KI. I changed playlists. Now it's 230F, and here you can consider previous year class. Oh, I close this record and put it here. So if you miss some ideas, you can look at video and repeat it. So let's say check. Yes.
I have some problem with my calculation, so I was wondering if I have a consultation or I can just come to you.
Describe it and send me by mail.
By mail?
Yeah. Do you know my mail?
No.
No?
No.
It's impossible.
Do then. I will check and I'll send it again.
Just a moment. I this.
Okay.
Хаиду.